Right, so next we'll look at an example. Let d sub 2 be the Euclidean metric on two-dimensional real space. What does an open ball centered at the point 0, 0 with radius 1 in the Euclidean metric look like? The open ball centered at 0, 0 with radius 1 in the Euclidean metric is the set of all ordered pairs xy in two-dimensional real space, such that the distance in the Euclidean metric from 0, 0 to xy is less than 1. So we have the norm of 0, 0 minus xy is less than 1. This is the norm of the negative of the point xy, or the vector xy. So this is the norm of the point xy, or alternatively the vector whose coordinates are x and y. So less than 1, the norm is less than 1, so this is simply the interior of the unit circle centered at the origin. So in the plane, open balls in the Euclidean metric are circular, the interior of circular disks. All right. So now we'll define a new metric on finite dimensional real space. The metric d sub 1 being the sum of difference of the absolute value of the difference between components is called the little L1 metric, or the taxicab metric. So we need to prove that this is, in fact, a metric. Once again, non-degeneracy and symmetry are trivial. We will show that d sub 1 satisfies the triangle inequality. The distance from between x and y in the metric d sub 1, or d sub 1 of xy, is the sum from I equals 1 to n of the absolute value of x sub I minus y sub I. This is the same as the sum from I equals 1 to n of the absolute value of x sub I minus z sub I plus z sub I minus y sub I. Which is less than or equal to the sum from I equals 1 to n of the absolute value of x sub I minus z sub I, plus the absolute sum from I equals 1 to n of the absolute value of z sub I minus y sub I. That is d sub 1 of xy is less than or equal to the sum of d sub 1 of xz plus d sub 1 of zy. So this is indeed a metric on finite dimensional rule space called the L1 metric or the taxicab metric. So once again, we'll look at an open ball in this metric in the real plane. So let d sub 1 be the taxicab metric. On two-dimensional rule space, that is the plane. What does an open ball centered at the point 0, 0 with radius 1 in the taxicab metric look like? The open ball centered at 0, 0 with radius 1 is the set of all ordered pairs xy in the real plane, such that the distance in the metric d1 between 0, 0 and xy is less than 1. That is, the sum of the absolute value of 0 minus x plus the absolute value of 0 minus y is less than 1. This is the sum of the absolute value of negative x and the absolute value of negative y, which is the same as the absolute value of x plus the absolute value of y. So in the first quadrant, x and y are both positive. So this inequality becomes x plus y is less than 1, which gives us the equation y is less than negative x plus 1. In the second quadrant, x is negative while y is positive, and so this inequality becomes negative x plus y is less than 1, which gives us the equation y is less than x plus 1. In the third quadrant, both x and y are negative, and so this inequality becomes negative x minus y is less than 1, which gives us the equation y is greater than negative x minus 1. And in the fourth quadrant, x is positive while y is negative, and so we have x minus y is less than 1, which gives us the equation y is greater than x minus 1. So if we now graph so in the first quadrant, we have everything below the line negative x plus 1. In the second quadrant, we have everything below the line x plus 1. In the third quadrant, we have everything above the line negative x minus 1. And in the fourth quadrant, we have everything above the line x minus 1. So this is the interior of the rectangular region, whose vertices are 1, 0, 0, negative 1, negative 1, 0, and 0, 1. All right. So we'll define a new metric. On finite dimensional rule space, the metric d sub infinity, which is the maximum value of the absolute value of the difference of the components, is called the square metric. So we need to prove that this is, in fact, a metric. Non-degeneracy and symmetry are trivial. We will show that the square metric, or d sub infinity, is or satisfies the triangle inequality. So d sub infinity of x, y is the maximum or the largest value of the absolute value of the difference of the components. So this is the absolute value of x sub alpha minus y sub alpha for some alpha being from 1 to n. And so this is the absolute value of x sub alpha minus z sub alpha plus z sub alpha minus y sub alpha, which is less than or equal to the absolute value of x sub alpha minus z sub alpha plus the absolute value of z sub alpha minus y sub alpha. Now, the absolute value of x sub alpha minus z sub alpha is less than or equal to the largest of the difference of those components, x sub I minus z sub I, and the absolute value of z sub alpha minus y sub alpha is less than or equal to the largest of those absolute values between the components x, z and y. And so we do in fact have that d sub infinity of x, y is less than or equal to the sum of d infinity of x, z plus d infinity of zy. So the triangle inequality does hold, and so this is in fact a metric on finite dimensional space, real space, called the square metric. So let d sub infinity be the square metric on two-dimensional real space, so in the plane again, and we look at what does the open ball centered at the point 0, 0 with radius 1 look like. The open ball in the square metric centered at 0, 0 with radius 1 is the set of all ordered pairs x, y in two-dimensional real space, such that the distance in the square metric between 0, 0 and x, y is less than 1. And so we have the maximum value of 0 minus x and 0 minus y is less than 1. That is the maximum value of the absolute value of x and the absolute value of y is less than 1. And so the absolute value of x is less than 1 and the absolute value of y is less than 1. So x can range between 1 and -1, and y can range between 1 and -1. And so this is the interior of a square region, and that is the square centered at the origin, or whose sides have midpoints at 1, 0, 0, -1, -1, 0, and 0, 1. Now, for you physics students out there, or for anyone who has a general interest in the geometry of space-time, I'll mention another interesting metric on finite dimensional real space, the Minkowski metric. On finite dimensional real space is given by d sub lambda is the lambda-th root of the sum from I equals 1 to n of the absolute value of the differences of the components to the power of lambda. So notice that lambda equals 1, or if lambda is 1, then this gives the taxicab metric. If lambda is 2, then this gives the Euclidean metric. And if lambda is infinity, and here we mean limiting value, then this gives the square metric. Now, what I'd really like you to notice at this point is that in finite dimensional real space, we'll compare the three metrics. The taxicab metric is the sum of the absolute value of the differences of the components. The Euclidean metric is the square root of the sum of the square of the differences in the components. And the square metric is the largest of the absolute value of the difference of the components. And so in one-dimensional real space, so in the real line, the taxicab metric is the absolute value of the difference in x and y. That is, it is the standard metric on the real line. The Euclidean metric is the square root of the square of the difference, which is the absolute value of the difference. So again, we have the standard metric on the real line and the square metric is also the standard metric on the real line in the case of one dimension. So this suggests that these three metrics are equivalent, and in fact we will prove that these three metrics generate the product topology on finite dimensional real space. And of course in finite dimensional real space this is the same as the box topology.